In this lecture, we're going to discuss some typical properties that a function can have. And in particular, we're going to look at three properties. So a function can be injective, or it can be surjective, or bijective. Okay. And bijective essentially is just going to mean it's both injective and surjective. So let's start with these two. So what does it mean? So function f from, let's just say, from some set A to some set B. So A is my domain, B is my codomain. It is called injective. Let's do it down here. So injective if and so there are a few ways to say this, actually. Let me start with the more technical mathematical definition. And then I'll write one after that. It's a little bit easier to understand. So what this technically means is for every pair of elements in my domain, so for every A1 and A2 and A, if f of A1 equals f of A2, so I'm going to do an implication here, actually. So if f of A1 equals f of A2, so if A1 and A2 actually map to the same element over here, that means that actually A1 and A2 had to be the same element. So A1 is actually just the same as A2. A1 is equal to A2. So that's what it means to be injective. For every A1 and A2 and A, you have this implication. Okay, there's a much more down-to-earth way to think about this. I did want to start with this, though, because when we actually prove functions are injective, this is what we're going to use. But yeah, so another way to say this, or there aren't, I'll define injective by what it's not. So a function is injective if there aren't two different elements of A mapping to the same element in B. Okay? To the same element of B. So here's an example. Let me just draw out an example quickly. So let's say I have some elements over here and some elements over here. This could be A and this could be B. Here's what I want to avoid. So maybe this one goes there. Maybe this one goes there. And then maybe this one goes there also. This is a perfectly good function, right? Because I have exactly one arrow coming out of everything in A. However, if I look at this part here, I have two different elements mapping to the same thing. So this is actually not injective. This is not an injective function. So an injective function is a special kind of function. It needs to satisfy this property. And this is how to think about it. Another way you can write this is every element of B is mapped to at most once. I can't have two different arrows coming into any element over here. So that's the way to think about it. Everything over here, there can be at most one arrow. If I have some element that doesn't get mapped to at all, that's okay, right? That's not what's preventing it from being injective. It's really this that we're looking to avoid. Okay. So that's injective. What does surjective mean? By the way, I just want to point out, so why is this the same as that? Well, I think it's essentially the contrapositive, right? So what's the contrapositive of this? It would be, and remember, the contrapositive of a true statement is equivalent. So it's the so you reverse the order here. So you say A1 is not equal to A2. That needs to imply what? It needs to imply that f of A1 is not equal to f of A2. Okay, so I start with two different elements. That's the A1 not equal to A2. there aren't two different elements mapping to the same element. So they cannot map to the same element. Whatever they map to have to be different, right? So that's how to think of injective. Okay, a function is surjective if, and again, I'll give you the technical definition first, which that we're going to use to do proofs. So it means that for every element over here, so for every b and b, there exists something mapping to it. So there exists an a and a such that f of a is b, f of little a is little b. Okay, that's what it means to be surjective. Or I could say, and you might say, this looks completely different than this, right? And it is in some sense, right? Like that. This whole thing, there's no implication here. There exists here, so this just looks totally different than that. However, it turns out these are sort of two sides of the same coin, actually, and that'll be more obvious after I write it in this way. So every element of B, right, for every element in B, there's something in A that maps to it. So what I can say is basically something exactly like this last line. However, I'm going to replace at most once with at least once. There has to be at least one thing mapping to it. There might be more. Okay, so that's another way to say what surjective is. Okay, if we look at this function here, well, I put another dot in there. So this is actually not surjective because see that dot there, nothing's mapping to it. But I need everything over here to get hit at least once for it to be surjective. Okay. Without that dot, it would be surjective. This is a surjective function, but not an injective function. But let's actually get a little practice with this. So, So just notice this is what I mean by they're sort of two sides of the same coin. Okay, you literally change one word. So you change at most once to at least once, and you actually. You go from injective to surjective. They are rather different concepts, though. So let me note the following. So note these are not actually exclusive concepts. So what do I mean by that? You could be surjective. And not injective. You can be injective and not surjective. You can be neither injective nor surjective, and you could be both injective and surjective. So those are all possible. Let me illustrate that maybe. Let's make a little chart here. So let's do it like this maybe. Okay, and I'm going to show you an example of all of those. So let's go here and then down here maybe, and draw these far down enough. So maybe on the top, I'm going to say we can either be injective or not injective. So I'll just say injective, question mark. This will be the yes column. This will be the no column. And over here, we can say surjective. Is it surjective? This will be the yes row, and this will be the no row. And I'll show you I can actually create an example of all of these. So maybe I'll do I think these kind of diagrams are easiest to think about. So let's have an A and a B. And let's just go ahead and draw all four of them. A and B. We can have A and B here, and A and B here. A and B. And so let's do a function that is both injective and surjective. What does that mean? You really want. This is the kind of concept it takes some time to really get used to these. And I know when I first learned this, a common mistake is I would mix them up. So you want to figure out some way to get these straight. But yeah, what does it mean to be injective? It means we do not have anything like this. Two things going to one dot. I have to draw something out of here. I've got to draw something out of here too, so I better not go there. So let's go there. This is injective, yes. It's also surjective because I hit everything here, right? Let's do one that's not injective but is surjective. So how do we do that? Well, to make it not injective, I actually do want to hit one thing multiple times, so like that. That's not injective, but it is surjective because notice I only drew one dot in here. If I had drawn another dot, then I wouldn't be able to do it, I don't think. But I only drew one dot, so yes, everything in B gets hit at least once. So this is surjective. If we want to do not surjective, let's think about how to do that. Well, I think I might need something extra over here. So we're going to do that. And yeah, I think this is an example of injective. It is injective. Don't let this fool you that you have two things. You don't necessarily need there to be two elements here. It's okay for it to be one element. It's saying for every pair of A1 and A2. So I don't have any choice. I mean, it's the same A here. So for that element in itself, if they're equal over here, then the element was equal over there. But yeah, that's true. But this is not surjective. See, because I missed that one. It's not true that for every B and B there exists something mapping to it. Is that one there? There's nothing mapping to it. So it's not surjective, but it is injective. If we want to do neither, then, well, let's have both these going there. That makes it not injective, and then we'll just have nothing going to there. So it's not surjective either. So those are some examples. It's a good idea to kind of stare at this for a while until you really make sure you understand why each of these is where it is. And try to come up with some examples on your own. But yeah, so a function that is yeah, let's write it down here. So a function that is both surjective and injective. As I mentioned before, we have a special name for that. Both surjective and injective is called bijection. Bijective, or a bijection. Yeah, is called bijective is the adjective, or a bijection. These are very important in mathematics, so we're going to be using these a lot for the rest of the course. But essentially, I mean, what's the other way to think of a bijection other than it's surjective and injective? If we look at these last things, so injective means every element of B is mapped to at most once. Surjective means every element of B is mapped to at least once. What would it mean to satisfy both of those things? Well, the only way for that to happen is if every element of B, or every element of B is mapped to exactly once. So every element of B is mapped to exactly once. Okay, so there's our bijection up here. It's the yes section, right? So this is also this one here is a bijection. Okay, excellent. Okay, well let's just talk really quickly about how do you actually prove functions have these properties. So yeah, how do you prove a function is injective? How would I do that? Okay, so what would I do? You might be able to figure it out, especially if you've been following along in the course. So how would I prove a statement like this? Well, I need to show it for every A1 and A2. So I'm going to start by taking an arbitrary A1 and A2. So here's how I start. Let A1 and A2 in A be arbitrary. And then what am I going to do? I need to prove an implication. See, I'm not trying to prove. Be really careful with this definition. I'm not proving f of A1 equals f of A2. Right? I'm not proving that. I mean, if that were it, like, I feel like that would be very restrictive. That would only allow constant functions essentially. But yeah, I'm proving the implication. If f of a1 equals f of a2, then, right? So if this thing, then a1 equals a2. So how do I prove an implication? You prove it by assuming this is true and then trying to prove that, right? And let this be arbitrary and we're assuming that f of a1 equals f of a2. Okay, that is the setup. That's how you start. And then what do? I want to try to show that, right? So you do some steps. So then you try to show, and this is going to be different for every problem. But you've got to know where to start at least. So that's how I would start. And then I have to show a1 equals a2. Let's do an example. So again, it's going to be a little different for every problem, but let's prove that. Let me think of a good injective function. So prove that the function, a function from, let's do r to r, given by, do one with the formula. F of x is e to the x. That's a good injective function. Exponential. Let's try to prove that it's injective. Okay. And there are different ways you can prove this. Let's try to do it straight from our definition to get some practice actually using this. Okay. So this is going to be our setup. We start by taking an arbitrary a1 and a2 in my domain, right? I start with arbitrary two things here. Not an arbitrary two things here because we don't even know if those can be written as f of something, right? They might not be in the range. So we start with a1, a2, and a. So what would that be in our example? You start over here with, so I let, here's our proof. I'm going to let x1 and x2, I'll call it, be in R. And what am I assuming? I'm assuming that f of x1 equals f of x2. And so I'll suppose that f of x1 equals f of x2. But what's our f? I mean, f is e to the x, right? So i.e., I can say what that means. I'm assuming that e to the x1 equals e to the x2. That's what I'm assuming. That's my starting point. What do I want to prove? I want to actually prove that x1 equals x2. Right? That these had to be equal to start. Okay? So I just want to emphasize, even though this is not the most intuitive definition, this is the most useful way to write a proof, actually. This is the easiest way to prove something is injective, usually, because it's very tangible. So this is what I'm assuming. How do I show x1 equals x2? I mean, I guess the idea would be to take logarithms, right? So let's say, so take logarithms of both sides. Take logarithms, right? Because that'll cancel the exponential. So I get this equals natural log of e to the x2. And it is true, actually, in the real numbers, the natural logarithm defined over at least the real natural logarithm, that this is just natural log of e to anything is just that thing, right? So it's really sort of a true inverse function. We'll talk about the inverse functions in a lot of detail later, but yes, you can take logarithms, that cancels it out, and we just get x1 equals x2, and that's what we wanted to prove. Okay. You have to be very careful with this kind of thing, though. So, for example, if we had the complex exponential, if we replace this with c and c, then this logic actually doesn't work. Because you can't define an inverse function, globally at least, over the complex numbers for the exponentials. Maybe we'll get into that later. But in any case, you have to be careful with this kind of argument. Let me show you a case where it doesn't work. So what's an example of a function that's not injective? So yeah, let's just say, so note, this kind of argument, so this same argument doesn't always work. Well, it doesn't work for the function we saw last time. It doesn't work for x squared. Let's call it g of x is x squared. It does not work for this because let's say we try to take x1 and x2 such that f of x, g of x1 equals g of x2, so x1 squared equals x2 squared. Let's say we start with that. Does that mean that x1 equals x2? Well, what if we take square roots? All right, using the same idea that we just used. If we take square roots, well, square roots cancel the squares, so you might think it's this. However, this is actually not true. That's not true. So yeah, this is not necessarily true. In fact, the square root of x squared is not x. It is the absolute value of x. Because if I took a negative number and squared it, that would erase the negative. Yeah, now I take the square root, that's just going to be the positive square root. So you have to be very careful of this type of thing. It's because this function is not, it doesn't have an inverse function. Square root is not the true inverse function of the squaring function. And we see actually, G is not injective. How do you prove it's not injective? That's easier, usually. How do you prove it's not injective? What would the negation of this be? It would be if there exist two things in A, right, such that they're they map to the same thing, but they're not the same element, right? So you need two different elements mapping to the same thing, and we can do that, right? Here's an example. If I take 2 squared, that's 4, but if I took negative 2 squared, that's also 4. See, so I have two different x values mapping to the same y value. That's no good. It's not injective. Okay, that's enough for injective for now. Let's see. What do we have left? Let's quickly discuss how would I prove a function is surjective. You might be able to figure that out by staring at the definition. But let's spell it out. So how do you prove a function is surjective? Again, there are multiple ways to do it, but let's just try to do it right from the definition. So here's what we do. We show that for every b and b, so I'm going to take an arbitrary b and b. I need to show there exists something interesting. So I need to actually produce an A, a little a and a. That maps to B. So that's the idea. So how do I show surjective? You let B and B be arbitrary. B and B be arbitrary. And then try to produce or come up with an A. An A such that f of A equals B. Okay. So that's how you prove it's surjective. To prove it's not surjective, I suppose you would try to find something that in B that is for everything in A it does not map to that. So, but yeah, let's try to prove that. Let's come up with a surjective function. Actually, yeah, let's just point out. So first example, e to the x, our function from before, is not surjective. Why? Is not surjective. Why? I should repeat all of what I wrote before. So I'm talking about from R to R. Always specify a domain when you're writing a function. It was bad of me to not do that. So our domain is R. This is not surjective. Why? Because essentially e to the x is always positive. Is always positive. Right? So for example, e to the x will never equal -1. This type of thing is not solvable. Okay, that means there are things in my codomain that are not mapped to by anything in my domain. Okay, does that make sense? So there's no such x such that e to the x is equal to -1. At least over maybe a couple of you are yelling at your screen right now. At least over the real numbers. This actually is solvable over the complex numbers. Actually, e to the x is very close to being surjective if we replace r with c. One of the things that there's actually infinitely many numbers that map to -1. But the most famous one is I pi. E to the I pi equals -1. You might think this is completely crazy, but yeah, this is a true statement. If you haven't seen this before, yeah, hopefully this will make you want to look into complex analysis. Yeah, maybe we can talk about that more later. But in any case, that's not surjective. Can we come up with a surjective function? How about the natural log? So the natural log, let's be careful to specify our domain correctly. So it's going to be all of the positive real numbers. So I shouldn't do that one. I should do this one, actually. So everything's starting at 0, but not including 0. So we're defining a function from the positive real numbers to just all the real numbers. Defined by, here, I'll mix up my notations. I'll do this notation. So this function, x goes to the natural log of x, is surjective. Let's prove it. So how do we prove it? We take something over here and we let it be arbitrary. So let's take an arbitrary, so let y and r be arbitrary. Right? So I'll just write out my thought process. We want to now produce. We want to find an x in here, right? Such that natural log of x. My writing's getting really messy. Such that the natural log of x equals that arbitrary y. So can we find such an x? I think, well, wait, how do we even do that if y is arbitrary? Well, just imagine y is some fixed number. Can I write a formula for the x that'll such that natural log of that x is y? Yes, I can, by essentially using the same idea as before. So we can do this. By letting, what do you think x should equal? Well, x should be e to the y. So y is that some fixed number. I'm going to take e to that number, which I can always do, because the domain of e is all the real numbers. That's important. So if I let x equal e to the y, then natural log of then the natural log of e to the y is y. Right? So natural log of x, but x is e to the y, and natural log of e to the anything is just that thing. So that proves that the natural log is surjective onto R. Okay. Okay, maybe we'll end there for now. We'll get some more practice with this in the next video.